There are places in the solar system that arrive in the mind already exaggerated. Some come to us through paintings, some through films, some through the old habit of imagining danger as density, as clutter, as noise. The asteroid belt is one of those places. It is often pictured as a crowded hazard, a wall of tumbling stone that any spacecraft must somehow dodge its way through. But the real asteroid belt is quieter than that, and stranger. It is not a barricade, nor a scrapyard. It's not the broken corpse of a planet in any simple sense. It is a sparse, ancient region between Mars and Jupiter, filled with remnants that should not be able to tell us as much as they do. And yet they do, because what survives there is not random. It is the product of loss, stirring, collisions, migrations, and time. It is a record written not in pages, but in absences, in families, in tilted orbits, and in the stubborn survival of bodies that have been altered without being erased. And tonight, we'll follow that record gently, one calm detail at a time. Good evening and welcome in. I'm Madeline Rowe, and tonight we'll take a slow, relaxing journey through the asteroid belt and the quiet science hidden inside it. And if these calm, evidence-based case files help you unwind, please subscribe, and there'll be another one waiting for you soon. Back in my office, it's quiet. A small lamp warms the desk, and beneath it sits a folder labelled simply Asteroid Belt. It is not a glamorous label, and it doesn't promise a blaze of revelation. It promises fragments, spacing, and a pattern you only notice once you stop expecting a crowd. The office itself feels a little like the subject tonight. Not full, exactly, just arranged. A chair here, a cabinet there, a few objects keeping their distance, each one telling you something about the room because of where it is and where it is not. I look down, open the folder, and turn to the first page. On evenings like this, that feels like enough to begin. As we proceed, it helps to clear away the most persistent image first. The asteroid belt is not a place where rocks are packed shoulder to shoulder. If you could move through the main belt in a spacecraft, you would not find yourself weaving constantly between looming boulders. In most of the belt, the distances between sizable objects are immense. The real thing is mostly space. The drama comes not from congestion, but from context. A broad band between the orbits of Mars and Jupiter contains bodies of many sizes, from dwarf planet scale down to fragments and dust, and the total mass of all those asteroids put together is still less than the mass of Earth's moon. That fact alone is enough to reset the whole picture. A region that occupies such a grand stretch of the solar system contains surprisingly little material. And once you realise that, the real question is no longer why the belt is there. The real question becomes why so little is left, and why what remains looks the way it does. That change in emphasis matters. It changes the asteroid belt from scenery into evidence. If the belt were simply a warehouse of leftover rocks, the subject would be interesting in a modest way, and probably not much more. But the belt is not merely leftover, it is sculpted leftover. Its present structure is awkward in ways that demand explanation. The bodies there are not all on neat, calm, nearly circular paths. Many have significant eccentricities, meaning their orbits are more stretched than a tranquil early disk would suggest. Many have notable inclinations, meaning they are tilted relative to the flat plane in which we expect planets and planetesimals to have formed. The belt also contains a distribution of compositions that is not fully tidy. There are broad trends with distance from the Sun, yes, But there is also mixing, complication, and overlap. And the whole region is astonishingly underweight compared with what older formation pictures would have expected. Those three clues, the excitation of the orbits, the imperfect sorting of composition, and the severe shortage of mass, are what make the belt such a powerful witness. Before following those clues, it is worth settling into the place itself. The main asteroid belt lies, broadly speaking, between Mars and Jupiter. The densest population is often described within a band from a little over 2 astronomical units from the Sun to a little over 3 astronomical units, though the broader region is often discussed a bit more loosely. 1 astronomical unit is the average distance from Earth to the Sun, so we are dealing with a zone several hundred million kilometers out. A middle territory in the inner solar system, but already beyond the familiar orbit of Mars. This is not the outer darkness of Neptune or the Kuiper belt. It is not the inner furnace of Mercury. It is a middle ground, warm enough to have mattered chemically, cold enough for different materials to become more common with distance, and close enough to Jupiter for that giant world's gravity to matter profoundly. Historically, the asteroid belt entered human knowledge through discovery that seemed, at first, to support a very simple idea. In the early 19th century, astronomers found Ceres, then Pallas, Juno, and Vesta in the region between Mars and Jupiter. For a while, it was tempting to imagine that here was a missing planet, or perhaps the remains of one. The notion is understandable. If there is a gap between planets and a set of bodies in that gap, perhaps they were once one thing. Human beings have a fondness for neat before and after stories. We like a world whole, then broken. But the more the belt was studied, the less satisfying that story became. The total mass is too small. The present orbital structure is too complex. The bodies are too varied. In the modern view, the asteroid belt is not best understood as the debris of one destroyed planet. It is better understood as the record of a region where planet building did not proceed to completion in the way it did for Earth or Venus, and where later gravitational and collisional history stripped, stirred, and rearranged the survivors. Even that phrasing needs care. When people hear that the belt is a place where a planet failed to form, they sometimes picture material trying earnestly to gather, only to be constantly interrupted, as though Jupiter were a cosmic nuisance swatting away every hopeful little world. There is some truth in the broad outline. Jupiter's gravity is a central reason the region did not become a large planet. But the real story is more subtle. The early solar system was not a tidy workshop. It was a disk of gas and dust, then of growing solids, then of planetesimals and embryos, then of migrating giant planets, resonances, scattering, heating, collisions, and loss. The asteroid belt's present condition is likely the cumulative result of several phases of history rather than one single veto delivered from afar. When scientists use the belt to test models of solar system formation, they do so precisely because any successful model has to explain not only why no planet sits there now, but why the belt that remains is dynamically excited, compositionally structured yet mixed, and drastically depleted. The phrase dynamically excited sounds almost lively enough to wake a listener, but it can be understood very calmly. Imagine setting a collection of marbles on a large, perfectly flat turntable, each marble moving in a tidy, circular path with very little tilt. That is a rough, emotional picture of a cold, orderly beginning. Now imagine that something disturbs the arrangement over time. Some paths become slightly stretched. Some tilt upward or downward relative to the original plane. Some marbles are nudged away entirely. The collection is still a collection, but it now carries the memory of disturbance. The asteroid belt is like that. Large asteroids today occupy a wide spread of eccentricities and inclinations. They are not all running wildly in every possible direction, but they are far more stirred than an untouched primordial disk should be. So something, or several somethings, had to do the stirring. Then there is the matter of composition. For a long time, the asteroid belt seemed to offer a satisfyingly clean map of temperature in the early solar system. Asteroids in the inner belt were more often of the stony, silicate-rich S-complex type. Farther out, darker and more primitive carbon-rich C-complex bodies became more common. Beyond that, still more primitive populations such as P and D-type bodies are associated with the farther outer regions and with related small body reservoirs. This broad trend still contains truth. It is not nonsense. It reflects a real large-scale pattern. But like many first drafts in science, it was too simple. As surveys improved, more asteroids were found, more spectra were taken, and the picture softened from a clean gradient into something more textured. Bodies did not remain perfectly segregated by birthplace. Smaller populations, especially, showed more mixing than the old textbook version would have implied. And once that mixing becomes clear, the belt starts to look less like a frozen original arrangement, and more like a population that has been repopulated, shuffled, contaminated, and sculpted. The third clue is the one that often changes how the whole subject feels. The belt today is tiny in mass compared with what older, more straightforward models of planet formation would have expected to occupy that region. If you extrapolate from the material needed to form the terrestrial planets on one side and the giant planet core region on the other, the primordial zone where the asteroid belt now sits might once have been expected to host roughly an Earth mass of material, give or take. What is actually there today is only a tiny fraction of that. Modern estimates for the total belt mass are on the order of a few 10,000ths of an Earth mass. However one states it, the conclusion is the same. The belt is drastically depleted. Not just modestly trimmed, not politely reduced, stripped down by orders of magnitude. And that means one of two broad things must be true, or perhaps some mixture of both. Either the region began with much more material, and then lost almost all of it very early, or it never held as much material there as some older models assumed. That distinction has become one of the central tensions in asteroid belt science. Was the primordial belt massive and later emptied, or was it comparatively sparse from early on? Each answer pulls the rest of the solar system with it, because the asteroid belt is not an isolated puzzle. It sits right beside another famous question: why is Mars so small? Mars is often described as undermassive compared with what simpler accretion scenarios once tended to produce. So the same family of models that tries to explain a low-mass asteroid belt often also tries to explain a low-mass Mars and the broader architecture of the inner solar system. This is one reason the asteroid belt matters so much. It is not a side note, it is a constraint. If your theory can make Earth and Venus but cannot explain Mars and the asteroid belt, the belt quietly informs you that your solar system is too elegant to be true. Because this is a case file for sleep and not a courtroom cross-examination, we can let these different models arrive one at a time, without rushing them. The oldest class of ideas leaned on resonances sweeping through the belt as the gas of the protoplanetary disk dissipated. Resonances are one of those beautiful astronomical concepts that sound abstract until you notice how physical they are. A resonance is, in essence, a repeated gravitational rhythm. If a small body finds itself in the wrong repeated timing with a giant planet, the tiny tugs can add up. In the asteroid belt, Jupiter is the major musician in the room. Certain orbital periods line up with Jupiter in simple ratios, and those locations can become unstable over time. These are part of what give us the famous Kirkwood gaps, the underpopulated lanes in the distribution of asteroids' semi-major axes. But early resonance sweeping models, on their own, struggled to reproduce the full observed structure of the belt, especially its inclinations. They were important steps, but not the last word. The Kirkwood gaps themselves are worth lingering with, because they are one of the clearest examples of the belt being more like a pattern than a pile. If you make a histogram of where asteroids sit by orbital distance, you do not get a smooth hill. You get missing lanes, hollows carved into the distribution where simple commensurabilities with Jupiter lead to long-term instability. An asteroid that keeps finding itself in the wrong beat with Jupiter can have its orbit altered until it is shifted away or driven into a path that no longer remains in the main belt. The gaps are not literal empty tunnels through a dense sea of rocks. They are dynamical signatures. They tell you that gravity does not need to touch every object at once to write a visible structure. It only needs time, repetition, and the right geometry. The belt is full of that kind of writing. Another family of models imagined the asteroid belt region as once containing not only small bodies, but also larger planetary embryos, Moon to Mars-sized objects moving among them. In this picture, those embryos stir the smaller asteroids through repeated gravitational encounters, exciting eccentricities and inclinations, and helping remove mass from the region while terrestrial planets form elsewhere. This general idea, often associated with the Wetherill-style framework for the early inner solar system, had real explanatory power. It linked the belt to terrestrial planet formation and offered a mechanism for violent early sculpting. But it, too, faced difficulties. To reproduce the observed belt well, the details matter. How many embryos, how long they last, what parts of the belt are overexcited, which inclinations survive, whether the resulting distribution becomes too unbalanced. Like many scientific models, it illuminated the problem brilliantly, even where it did not solve every part of it. Then came one of the most influential modern proposals, the Grand Tack. The name is nautical, and fittingly so. In sailing, a tack is a turn made to change direction relative to the wind. In this solar system version, Jupiter does not simply form and sit where we find it now. Instead, during the era of the gas disk, Jupiter migrates inward towards the Sun, and later reverses course, moving outward again after interacting with Saturn. In doing so, it ploughs through and then repopulates the asteroid belt region in a dramatic way. In the strong form of the picture, Jupiter's inward migration can effectively clear out the primordial belt, and its later outward migration can scatter back in some inner, stony populations, while also implanting more primitive material from farther out. And this has enormous appeal because it naturally addresses several constraints at once. It can help explain a low-mass asteroid belt, compositional mixing, and the truncation of material beyond about 1 to 1.5 astronomical units that is useful for making Mars small. What makes the Grand Tack so compelling in a sleep story sort of way is that it turns the asteroid belt from a simple leftover shelf into a place of traffic. Not traffic in the crowded sense, but in the historical sense. Bodies need not all be local. Some may be immigrants, some may be returnees, some may be the survivors of a route that no longer exists. The belt becomes less like a neighbourhood that stayed put, and more like an archive assembled after a period of motion. But influential is not the same as final. Even Grand Tack scenarios depend on details, and some of their outputs require later solar system events to finish bringing the belt into something like the observed state. The eccentricity distribution, for example, can come out too excited and then rely on later reshaping during giant planet instability phases. So the picture remains powerful, but not immune to revision. That later reshaping brings us to another major idea in modern solar system history. The notion that the giant planets did not always occupy their present arrangement, and that they underwent an instability or migration phase after the gas disk was gone. In broad terms, versions of the so-called nice model family propose that interactions among the outer planets and a trans-Neptunian disk rearranged the architecture of the outer solar system. For the asteroid belt, the key point is that later, giant planet evolution can further excite or deplete the belt without necessarily rewriting every aspect of its compositional structure. In some reconstructions, the belt suffers an additional significant loss of members during this later phase, and unstable resonant regions continue to drain afterward. That means the belt we see today may be the product of at least two major rounds of sculpting. An early one tied to terrestrial planet formation and giant planet migration, and a later one tied to giant planet instability and resonance sweeping in a newly rearranged solar system. A newer alternative, and one present in the research you attached, is the idea that Jupiter and Saturn in a near-resonant configuration could have chaotically excited and depleted material beyond about 1.5 astronomical units on timescales of several million years, helping to create both a small Mars and a low-mass asteroid belt without relying on the classic Grand Tack path in the same way. In that scenario, the asteroid belt is again not merely local residue. It becomes a mixed population of remnant local material and captured bodies from farther out, assembled after a period of strong excitation and depletion associated with the Jupiter-Saturn pair. What matters for our purposes tonight is not declaring one of these theories the single winner. What matters is understanding what they are all trying to honour. The belt is telling us that orbits were excited, mass was removed, and compositions were mixed. Any viable story has to listen to all three, and that is perhaps the most peaceful way to think about scientific disagreement here. It is not chaos, it is constraint. Researchers are not simply inventing increasingly elaborate cosmic stories because embellishment is fun. They are trying to match a demanding witness. The asteroid belt is stubborn. It does not let you explain the mass without the orbits. It does not let you explain the orbits without composition. It does not let you explain the composition while ignoring Mars. The reason there are multiple sophisticated models is not because the subject is fuzzy. It is because the evidence is unusually informative and therefore unusually difficult to satisfy all at once. There is another quiet reason the belt has become such a demanding witness. Scientists often focus especially on the largest asteroids when trying to reconstruct the earliest stages of its history. The reason is not romance, but trust. The smaller the asteroid, the more likely it is to have been shifted over long times by thermal forces, altered by collisions, or produced as a fragment of something older. The largest survivors, by contrast, are more likely to preserve something closer to ancient structure. They are not perfect fossils. Nothing in a restless solar system is perfect. But as tracers of the early belt, the big bodies are often cleaner than the small ones. They carry fewer later fingerprints, or at least fingerprints that are easier to account for. So when astronomers ask what the primordial belt may have looked like, they often lower their voices and listen first to the giants that are still left. That, too, is a useful correction. The asteroid belt is not one democratic census in which every stone speaks equally well for the past. Some members are original citizens, some are grandchildren, some are chipped descendants of collisions that happened long after the first act of formation ended. Some are so mobile that their present address tells you more about their recent drift than their birthplace. The belt, in other words, has age structure and genealogical structure. If you want the oldest accent in the room, you do not always ask the smallest fragment. We can come back now from the theoretical corridors to the visible belt itself, because no matter what grand story one prefers, the present-day population is rich with smaller, quieter clues. One of the simplest is that not all asteroids are alike in physical history. Some are primitive, some were heated, some differentiated internally, meaning they became layered, with denser material sinking inward and lighter material staying nearer the surface, as though they were small worlds trying in miniature to become planet-like. Some were shattered, some were reassembled as rubble piles, some belonged to families created by catastrophic collisions, their orbital elements still preserving kinship long after the violent event itself. If the belt were only a bucket of pebbles, it would be less revealing, but it contains bodies that lived different kinds of lives. No two anchor worlds illustrate that better than Ceres and Vesta. Ceres is the largest body in the belt and also a dwarf planet, round enough under its own gravity to earn a special category. Vesta, by contrast, is the largest asteroid in the classic sense and a markedly different kind of object. If you wanted to explain the diversity of the belt without a single chart, you could do it by placing these two worlds side by side. Ceres is darkish, water-related in important ways, and represents a more primitive, volatile-rich branch of early small body history. Vesta is brighter, basaltic, and differentiated, a body that once got hot enough to melt internally and make a crust. They occupy the same broad region of the solar system, yet they are not variations on one simple theme. They are reminders that the belt contains survivors from very different thermal and compositional pathways. And even beyond those two, the belt refuses simplicity. Pallas travels on a notably tilted orbit, an early discovered world whose dynamical posture already hints that the largest bodies did not all settle into one clean arrangement. Hygiea, another large member of the belt, represents yet another branch of the population. None of these bodies alone explains the belt, but together they help break the old habit of imagining a single ladder of development. There is no one asteroid destiny. There are parallel histories, interrupted histories, heated histories, watermarked histories, and histories that survive mostly as fragments. Ceres has a way of softening the whole belt in the mind. It is easy to forget, when talking about asteroids, as if they were all dry stones, that some members of the broader population are associated with hydrated minerals, water-bearing histories, and primitive chemistry that links them conceptually to meteorites rich in carbonaceous material. Ceres itself sits at the threshold between asteroid belt science and dwarf planet science. It is large enough to be spherical, likely differentiated at least to some degree, and has long attracted interest as a world that preserves signs of water in one form or another. It is not an ocean world in the popular, dramatic sense often reserved for the outer solar system, but it does remind us that asteroid is not a synonym for simple. The belt contains not just rubble, but worlds with geologic stories. Vesta, meanwhile, is one of the most satisfying objects in the whole belt because it bridges telescope observations, spacecraft observations, collisional history, and meteorites found here on Earth. Long before NASA's Dawn mission reached it, Hubble had already revealed a giant impact basin dominating its southern hemisphere. Dawn later confirmed that Vesta bears colossal scars, including the enormous Rhea Silvia Basin. A major impact there blasted fragments into space, creating a population of smaller bodies, sometimes called Vestoids, and likely supplying a family of meteorites that eventually reached Earth. This is one of the rare cases in planetary science where the line of evidence can feel almost personal. A violence in the asteroid belt, hundreds of millions or billions of years ago, can leave fragments that cross space, survive atmospheric entry, and arrive in our laboratories as stones we can hold. That link between asteroid families and meteorites is one of the quiet miracles of the belt. When a collision catastrophically disrupts a parent body, the fragments do not scatter into meaninglessness. They begin with related orbital elements, and although those elements spread over time through resonances and non-gravitational forces, the kinship can still be detected. Families emerge in orbital parameter space, like surnames in a census. Some are old and diffuse. Some are young and sharp. Some are associated with clear compositional signatures. Others are harder to interpret. But together they tell us that collision is not just a rare interruption in the belt. It is one of the principal ways the belt renews its visible structure. It creates dust. It creates fragments. It creates pathways by which smaller bodies drift toward resonances and are eventually delivered into the near-Earth population. There is a lovely subtlety behind that family detective work. Astronomers do not usually rely only on an asteroid's instantaneous orbit, because an orbit at one moment is like the position of a leaf in a breeze. It is real, but it also includes temporary swaying. Instead, they often use what are called proper elements, quantities that capture the longer-term, more stable character of an orbit once the short-term oscillations have been averaged away. Those proper elements act a little like a family name that survives changes of weather. In that quieter orbital space, relatives can be seen more clearly. A catastrophic breakup that would look chaotic in a movie can, over time, still leave a mathematically detectable cluster. The belt, once again, is less about spectacle than about pattern. And pattern comes with loss. One of the more melancholy truths in asteroid science is that many of the earliest collisional families are probably gone as recognizable families. Not gone in the sense that every fragment vanished, but gone in the sense that later excitation, slow drift, and the long wearing down of the belt dispersed them too thoroughly for us to identify them cleanly now. The families that remain most visible are often those that formed later, or those that were large enough to leave especially durable signatures. This means the belt's family album is incomplete. We do not see every ancient catastrophe. We see the younger names more clearly than the first ones, but even that incompleteness is informative. It tells us the belt was dynamically busy enough, and enough later time has passed, that early records have been blurred. This is where the Yarkovsky effect enters with a kind of patient subtlety that suits the hour. A small asteroid warmed by sunlight does not simply sit there as a passive stone. It absorbs solar energy and re-radiates it as heat. Because of rotation and timing, that thermal emission can act like a tiny thrust. Over long timescales, especially for smaller bodies, that thrust can slowly alter the semi-major axis of an orbit. Not dramatically, not in a way you could watch with your eyes, but enough, over millions of years, to nudge fragments from a family toward resonances. Once there, resonances with planets can do the rest, pumping eccentricities until the object leaves the main belt and becomes a near-Earth asteroid or a meteoroid on an Earth-crossing path. In other words, the belt is not just an archive, it is a source region. It leaks, slowly and continuously, through well-understood dynamical channels. And once you know that, a second quiet force begins to matter too. Yorp, the way sunlight acting on an irregularly shaped small body can slowly change its spin state. Some asteroids spin up, some slow down, some alter the tilt of their spin axes. Over long enough times, this can reshape the small body population in delicate ways. A fast rotating rubble pile may begin to shed material. A tiny moon may form. An odd top-shaped profile may emerge. What looks like a silent stone can, over immense durations, turn sunlight into structural change. The belt is full of processes like that, where nothing appears to happen, and yet the long arithmetic never stops. That is part of why rubble piles are so fascinating. Not every asteroid is a single coherent monolith. Some are gravitational aggregates, loose collections of fragments reassembled after disruption, held together more by weak self-gravity than by the strength of one intact rock. These bodies are reminders that the belt does not merely break things, it also reassembles them. Destruction in the asteroid belt is often partial, and aftermaths can become their own worlds. Some binaries likely formed through spin-up and shedding. Some contact binaries look like two survivors pressed gently together. The belt does not just preserve the memory of impacts, it preserves the strange improvisations that follow them. That leaking matters because it connects a sleepy story about a distant belt to the stones that fall through our own sky. Many meteorites ultimately trace their ancestry to main belt asteroids. The path is rarely direct or romantically simple. A fragment is broken loose, then drifts, then enters a resonance, then becomes a near-Earth object, then perhaps experiences collisions or orbital evolution, and only much later intersects Earth. But the origin remains. The rock in a museum case may be a message from the belt. An ordinary chondrite may connect to stony parent bodies in the inner belt. Howardite Eucrit diogenite meteorites likely connect strongly to Vesta. Carbonaceous meteorites preserve evidence of more primitive parent bodies, though matching exact meteorite classes to exact asteroids remains difficult and incomplete. The belt, in this sense, sends out samples of itself, though not evenly, and not without bias. Some materials survive delivery better than others. Some are too fragile. Some are too distant. Some are underrepresented in our collections, not because they are absent, but because transport and survival are selective. That selectivity is an important reminder against oversimplifying meteorites as a perfect inventory. We do not collect the belt in proportion to its true diversity. We collect what can be delivered and can survive. Even so, meteorites remain one of the most intimate ways asteroid belt science touches Earth. They give us isotopic clocks, mineral assemblages, histories of aqueous alteration, differentiation, shock, and thermal metamorphism. They tell us some parent bodies formed early, heated through radioactive decay, and melted. Others stayed more primitive. Some experienced water-rock interaction. Some were battered and brecciated. Through them, the belt stops being merely a remote orbital population and becomes a set of actual materials in human hands. And in a few extraordinary cases, the lesson becomes stranger still. Some meteorites appear to contain an unexpected diversity of materials mixed into a single small body, as though the early or later asteroid environment sometimes brought together lithologies that ought not to have been so intimately combined. That is a reminder that the belt's history is not only neat sorting and clean parent body genealogy. There were episodes, somewhere in the past, when different materials met under conditions we do not yet fully reconstruct. The archive is not only orderly, it contains puzzles stitched into the stones themselves. Collisions, then, deserve a little more of our attention because they are one of the few aspects of the belt that modern telescopes can occasionally catch in motion. The Hubble observations you linked are especially lovely for this. In one case, Hubble imaged a bizarre X-shaped debris pattern and trailing streamers that strongly suggested a head-on asteroid collision. The image is compelling, but what matters most scientifically is quieter than the image itself. It supports the idea that the asteroid belt is still slowly eroding through collisions, not exploding in some grand continuous chain reaction. Eroding, that is the right word. The belt today is not a battlefield in the cinematic sense. It is a long attritional process in which bodies strike, chip, disrupt, and rework one another across ages too long to feel violent in human terms. Another Hubble-observed object sprouted multiple dust tails, like a rotating sprinkler in space. Still, another system turned out to be a binary pair of asteroids showing comet-like activity. These observations are a useful antidote to rigid categories. Not every dusty tail belongs to a classic icy comet arriving from the far outer solar system. Some activity in the main belt is driven by collisions or by rotational shedding, or in certain cases by sublimation from bodies that preserve ice in more sheltered conditions. The borderlands between asteroid and comet are more interesting than the old diagrams suggested. But for tonight's purposes, the larger point is that Hubble helps us catch the belt in the act of becoming what it will be next. The belt is not merely ancient, it is ongoing. Those active asteroids and main belt comets open an especially gentle mystery. Where exactly was the snow line in the early solar system? And how much water-rich material belonged naturally in the asteroid belt, rather than being implanted later? A main belt comet is a body on an asteroid-like orbit that nevertheless shows comet-like activity, often through dust emission, and, in some cases, perhaps the influence of volatile loss. Their existence complicates the old image of a dry, stony belt sharply separated from a distant icy comet reservoir. If some main belt bodies preserve buried ice, then the belt is not just a desert of rock. It contains pockets of a colder memory. And if some water-rich bodies were delivered into the belt from farther out, then the belt also becomes a record of migration written partly in volatiles. That question matters for more than classification. It touches the deeper issue of where carbonaceous material formed, how water-rich those parent bodies truly were, and how the inner solar system may have received some of its volatile inventory. If main belt comets are closely related to the parent bodies of carbonaceous chondrites, then one picture of the early belt gains strength. If they are more akin to bodies implanted from a cometary reservoir, a different picture gains ground. The answer is still being worked out. But the very existence of the question enlarges the belt. It is not only a region of stones and scars. It may also be a zone where the story of water approaches, pauses, and leaves clues. If you step back from these individual cases, the belt starts to feel like a place governed by rates more than by events. There are collisions per unit time. There is drift per unit time. There is leakage into resonances per unit time. There is gradual depletion of unstable niches per unit time. And this matters when we think about the mass problem, because one tempting thought is that maybe the belt simply ground itself down collisionally from a once massive state to its current meager one. But the detailed collisional and dynamical constraints argue that collision alone cannot plausibly account for the full scale of depletion. If the belt had stayed massively populated while already dynamically excited for too long, the collisional consequences would be too severe. The scars, size distributions, and other constraints would not line up cleanly. That is one reason many researchers conclude that the major mass depletion had to happen early, and that the excitation and depletion were closely linked in time. That conclusion is elegant in its severity. It implies that the current belt is not the calm remainder of a long, gentle waste. It is the lucky residue of a much more dramatic early filtering. Most of the material that was ever in or associated with that region did not simply wear down into nothing while staying put. It was dynamically removed, scattered, ejected, driven onto planet crossing or sun grazing, or otherwise unstable paths. The survivors are the part that remained in long-term stable zones after the worst of the early sculpting had passed. Once you think of the belt that way, the emptiness no longer feels accidental. It feels selected. Selection also helps explain why the belt is such an excellent test case for planetary migration. If giant planets moved significantly, they would have perturbed small body reservoirs. They would have scattered some material inward, some outward, captured some populations, destabilized resonances, and left fingerprints in the distributions of orbital elements and taxonomic classes. The asteroid belt, the Hildas, the Trojans, even farther reservoirs can all act as archaeological layers of that migration history. In that broader context, the belt becomes less like a local neighbourhood and more like a customs record. It notes who passed through, who remained, who arrived late, and who no longer belongs where they once formed. There is a particularly calming kind of scientific humility in that sentence. No longer belongs where they once formed. It is a quiet way of admitting that present location is not destiny and not necessarily origin. In the old, simpler picture, bodies formed more or less where we see them. That has the comfort of a labelled shelf. The stony bodies belong inside, the darker, primitive ones belong farther out. But the modern view of solar system evolution is less shelf and more current. Material moves, planets move, reservoirs exchange members. Some of the most primitive populations in or near the belt may not have formed there at all. Some bodies in the inner belt may be survivors from once more local populations. Some interlopers complicate every neat diagram. The belt remains patterned, yes, but it is a pattern with traffic. To make that a little more tangible, imagine the early solar system not as a completed architecture, but as a room being furnished while the floorboards are still moving. Things placed carefully do not remain carefully placed. Heavy pieces alter the tilt of the room. Objects slide, collide, wedge against one another, and sometimes leave marks more durable than their own presence. By the time the room settles, some items are gone, some are chipped, some have migrated far from where they began, and the gaps tell as much of the story as the survivors do. The asteroid belt is full of those gaps, empty resonances, missing mass, missing large local populations that simpler accretion histories would have predicted. What remains is enough to reconstruct much of the rearrangement, but not enough to make the process feel obvious at first glance. This is one reason I find the belt so suitable for an evening story. It teaches a very calm form of inference. It says, do not confuse emptiness with lack of evidence. In astronomy, emptiness often is the evidence. A resonance gap is evidence. A missing Earth mass is evidence. A small Mars is evidence. A mixed taxonomic distribution is evidence. A family of fragments around Vesta is evidence. The belt is not loud, but it is articulate. It also invites a lovely correction to the habit of thinking of planetary formation as a ladder everyone climbs the same way. In reality, the solar system preserves bodies at many different levels of development. Earth became a planet with a layered interior, atmosphere, oceans, plate tectonics, and biology. Jupiter became a giant. Ceres became a dwarf planet. Vesta became a differentiated proto-planet-like remnant. Many other bodies remained smaller, primitive, or fragmented. The asteroid belt is where many of those unfinished or interrupted histories remain visible together. It is less a monument to failure than a museum of partial outcomes. That phrase, museum of partial outcomes, may be the right emotional centre for the whole episode, because the belt is full of bodies that did not all fail in the same way. Some never became large enough to differentiate. Some did, then were broken. Some may have preserved ice or hydrated minerals. Some became parents to meteorites. Some were implanted. Some were scattered. Some are so old and stable that their very continued existence constrains every model of dynamical chaos proposed for the early solar system. A museum, yes, but a museum in which the display cases are still colliding, drifting, and occasionally sending pieces to Earth. A moment ago, we mentioned Kirkwood gaps, and it is worth returning to them briefly, because they connect the broad gravitational story with the intimate experience of moving through the belt. If you were a small fragment slowly drifting under the Yarkovsky effect, you could spend millions of years in a fairly stable niche, and then, by tiny thermal pushes, arrive at the edge of a resonance with Jupiter. The resonance would not look like a wall. It would look like an invisible schedule that suddenly matters. Each orbit, a small timed tug. Each timed tug, a slightly altered eccentricity. Over enough cycles, the orbit becomes unstable enough to escape the belt. That is such a beautiful contrast to the science fiction version. No giant boulder chase, no desperate swerving, just a patient bookkeeping of gravity until a path is changed. The calmness of that process can hide how consequential it is. Many near-Earth asteroids are thought to originate from the main belt, delivered through resonant escape hatches. So the belt is not only a record of the early solar system, it is an active supplier of the small body population that matters directly to planetary defense. And yet, even here, the belt remains a nuanced source. Some Earth-crossing debris on comet-like orbits appears in significant size ranges to have main belt origins rather than truly cometary origins, showing again how orbital appearance can mislead if composition and dynamical history are not considered together. Categories blur, source regions overlap. The solar system likes to complicate any label we begin to trust too much. Another useful correction involves the word primitive. In asteroid science, primitive does not mean uninteresting or undeveloped in a dismissive sense. It means less thermally processed, closer in some respects to early solar system materials, rich in clues about original solids, organics, and water-bearing minerals. Primitive asteroids and meteorites are precious because they preserve chemistry closer to the beginning. Meanwhile, differentiated bodies like Vesta are precious because they preserve the story of early heating and internal evolution. The belt offers both. It gives us material that remained closer to a primordial state and material that moved partway toward planet-like complexity. Once again, it is a museum of alternatives. It is also a reminder that size changes everything. The broad taxonomic gradient is stronger among large asteroids than among smaller ones. Smaller bodies are more easily moved by non-gravitational effects. They are more often collision fragments. They are more likely to have been redistributed in ways that blur original patterns. So when astronomers reconstruct the early belt, they often pay special attention to larger asteroids, particularly those tens of kilometers across and larger, because these are more likely to preserve primordial or at least ancient dynamical information. Not perfectly, never perfectly, but better. The smaller you go, the more the modern belt becomes not just a record of where bodies formed, but of family creation, drift, collisional gardening, and dynamical remixing. That word gardening may sound too domestic for orbital mechanics, but it is useful. A garden is not static simply because it remains in one place. Surfaces get turned over. New growth appears from old roots. What looks old at a glance may be recent. The asteroid belt has that quality. A surface may be ancient in composition, but young in exposure. A family may be old or young. Space weathering darkens and alters surfaces. Collisions expose fresher material. Spin states change. Small moons exist around some asteroids. Contact binaries and rubble piles tell stories of reaccretion after disruption. There is no single asteroid condition. There are many, and each one is a clue to process. The Dawn mission, though we are not making this a spacecraft episode, deserves a gentle nod here because it sharpened two of the most important anchor bodies in the belt into proper worlds. Dawn turned Ceres and Vesta from distant telescopic subjects into landscapes. That changed the emotional truth of the belt. It is one thing to say that Vesta is differentiated and heavily cratered. It is another to actually see the immense basin, the layered geology, the strange topography. It is one thing to say Ceres is a dwarf planet with water-related minerals and enigmatic bright deposits. It is another to see the faceted face of that small world and realise that the belt is not only a region of objects, but a region of places. And once you admit that the belt contains places, the phrase leftovers becomes a little too casual. Leftovers are what remain on the plate after the meal. The asteroid belt is more dignified than that. It is leftover material, yes, but material that turned into environments, histories, scars, and classes of bodies with individual identities. Even the fragments matter. A shard from Vesta can teach differentiation. A carbonaceous meteorite can teach aqueous alteration or early solar system chemistry. A family distribution can teach collisional timing. A gap can teach resonance. A mixed taxonomic pattern can teach migration. In this region, almost everything is both itself and a clue to something larger. One of the loveliest larger things it teaches is that planet formation is not only an additive process. We often describe formation as accumulation, dust to pebbles, pebbles to planetesimals, planetesimals to embryos, embryos to planets. That is true as far as it goes. But the asteroid belt insists on the subtractive side of formation. Removal matters. Scattering matters. Erosion matters. Migration matters. In a sense, the final architecture of the solar system depends as much on what was taken away or displaced as on what accreted successfully. Earth exists in part because certain materials stayed and merged, but also because other materials were moved, lost, or never allowed to crowd the region for too long. The asteroid belt is where subtraction remains visible. This is also why the belt helps with the story of water on Earth, even if indirectly and with many caveats. Some models of solar system formation use the delivery of water-rich asteroid material to the growing terrestrial planets as an important ingredient. Carbonaceous bodies from farther out are natural suspects in parts of that story. The isotopic details are complicated. The relative roles of asteroids and comets are still debated in broader water delivery discussions, and no single simple tale should be forced on the evidence. But the key point is that the asteroid belt is not irrelevant to habitability. It preserves materials and transport pathways that connect directly to the composition and bombardment history of the inner planets. In that sense, the belt is a quiet participant in the prehistory of oceans. If all of this makes the belt sound overly important, that is because, in a certain precise way, it is. The planets are majestic, but they are also overbuilt. They have overwritten much of their earliest history through geology, atmospheres, tectonics, volcanism, impacts, and internal evolution. The asteroid belt preserves smaller bodies that did less overwriting. They are not untouched, far from it, but they are not as geologically self-editing as a planet like Earth. That gives them special value. In reconstructing the early solar system, sometimes the most useful witnesses are not the biggest ones, but the ones that never got the chance to become too complicated. And yet the belt's value is not only that it is old, it is that it is old and interpretable. The number of known asteroids has grown enormously through modern surveys. Spectral classification has become much richer. Infrared data, albedos, orbital catalogues, spacecraft encounters, meteorite studies, and numerical simulations all now talk to one another. The belt has gone from being a simple band of minor planets to being a high-resolution dataset for the deep past. That transformation in our knowledge is one of the real scientific stories of the last few decades. Not one dramatic discovery, but a gradual elevation of the belt from background feature to key constraint. And there is an especially elegant twist here. We do not only learn about the asteroid belt by observing the asteroids directly, we also learn about it by noticing what the whole belt does to everything else. The collective mass of the main belt, though small on planetary scales, still exerts a real gravitational pull. When astronomers and dynamicists build exquisitely accurate planetary ephemerides, the predictive models of where planets and spacecraft will be, they cannot simply ignore the many bodies of the belt. The largest asteroids are modelled individually, and the combined pull of the smaller remainder must be included as well. In that sense, the belt becomes part of the solar system's bookkeeping. It is too slight to dominate, but too real to omit. There is something I like very much about that. A region famous in popular culture for looking crowded turns out, in science, to matter not because of visual congestion, but because of cumulative subtlety. Hundreds of large asteroids and the unresolved background population together tug just a little on planetary motions. Spacecraft tracking near Mars and the long precision record of orbital calculations help refine estimates of that total influence. The belt is faint enough to seem negligible, and yet substantial enough that precision astronomy has to account for it. That feels like the belt's personality exactly. Understated, but never irrelevant. Once you know that, the office metaphor from the beginning becomes a little richer. A room need not be packed to have weight. A few carefully placed objects can change how the whole floor feels underfoot. The asteroid belt is like that. It is not full, but it is consequential. It does not dominate the architecture of the solar system, but it participates in it continuously. Even the empty-looking middle ground between planets has mass, rhythm, and consequence. When you look at the history of increasing resolution, there is a lesson there too. The first picture was not wrong so much as incomplete. Inner belt, stonier. Outer belt, darker and more primitive. Jupiter important. No planet form there. All of that remains broadly true, but better data turned the broad truth into a more demanding truth. The gradient became mixed. Jupiter's role became part of a larger migration history. No planet formed became a region was dynamically and compositionally sculpted, while planet formation elsewhere proceeded under related constraints. This is how science often improves, not by humiliating the old picture, but by asking it to survive more detail. There is something deeply restful in that. It means the universe does not require us to leap from error to certainty. It allows refinement. The asteroid belt used to be a sentence. Now it is a chapter. Someday it will be several chapters more, especially as new missions, telescopes, and sample studies continue to sharpen the connection between asteroid classes, meteorites, and dynamical histories. But even now, the belt already stands as one of the best places to test our stories of the solar system against surviving evidence. We can let the room grow a little dimmer now and think again about the office from the opening. A desk, a lamp, a few objects, each one meaningful partly because of how much empty space lies between them. The asteroid belt has that quality. It is not crowded, but it is not empty in the useless sense. Its separations matter. Its resonant hollows matter. Its surviving clusters matter. Its giant absences matter. A place can be sparse and still full of information. In fact, sometimes sparsity is what lets the information emerge. Take the old destroyed planet idea one last time. It survives in popular culture because it offers a satisfying singular cause. But the belt resists singular causes. It is too structured for pure explosion, too underweight for a simple missing planet, too mixed for strict in-place sorting, too dynamically excited for a quiet, untouched remnant, too rich in families and differentiated survivors for a one-note explanation. The real story is less theatrical and more profound. The belt is what remains after the early solar system passed through several filters: formation, migration, excitation, collisional evolution, resonance, and long-term stability. Not one catastrophe, but an ecology of processes. Perhaps the most surprising thing about that ecology is how much order it produces without calm. The belt is stirred, yet patterned, depleted, yet populated, mixed, yet still broadly graded, eroding, yet still supplying near-Earth objects, old, yet still changing. That coexistence of motion and structure is one of the most beautiful things in celestial mechanics. Disorder is not the end state. Repeated forces, even disruptive ones, can produce recognizable architectures. And so when we say the asteroid belt is a fossil record of the early solar system, we should be careful not to imagine a fossil as something fully dead and sealed in stone. The belt is more like a fossil coastline still being touched by waves. The oldest contours remain. New erosion happens, small collapses occur, sediment moves, yet the ancient shape is still legible. That is what makes the belt so compelling. It is both archive and process at once. There are listeners, I think, who prefer the giant planets, the moons with hidden oceans, the exoplanets with impossible weather. I understand that. The asteroid belt can seem modest beside them, but modest is one of astronomy's disguises. A small region of leftover worlds between Mars and Jupiter ends up constraining how we think the entire inner solar system formed. A collection of undergrown bodies ends up telling us about migration by Jupiter and Saturn, about the smallness of Mars, about meteorites in our museums, about impact histories on planets, about water-rich material moving inward, about how not all worlds stay where they were born. That is not a modest role. It is only modest lighting. The best science subjects for sleep often share that quality. They do not shout their significance at first, they unfold. The asteroid belt unfolds from misconception into measurement, from crowded rocks into dynamical evidence, from failed planet into sculpted relic, from minor planets into major constraints. And because the shift is so gentle, it leaves behind a very satisfying feeling. Not that something spectacular happened, but that something became clear. Clear, though, does not mean finished. There are still outstanding questions. How much of the compositional distribution can be traced directly to implantation from farther reservoirs? How much remained local? Which aspects of giant planet migration were most important? And when? Was the primordial belt ever truly massive, or was it relatively empty from very early on? How exactly do meteorite groups map onto asteroid classes and families? How much did later instability versus earlier migration shape the final orbital distribution? What fraction of water-rich belt bodies formed beyond the snowline, and what fraction belonged to a more local history? These are not small questions, they are active ones. But uncertainty here does not weaken the belt's importance, it strengthens it. The reason the questions remain alive is precisely because the belt is so informative that every serious model must pass through it. So perhaps that is the right final understanding before we drift toward the end. The asteroid belt is not an embarrassment in the solar system's architecture, not a place where building materials were forgotten. It is one of the system's most revealing achievements of non-completion, because a planet did not fully form there, because migration and instability did not erase everything, because collisions fragmented without pulverizing every clue, because some bodies remained large enough to preserve ancient histories. We are left with a region that can still speak, not plainly, not all at once, but reliably if we listen in the right way. The lamp on the desk has grown warmer now. The folder lies open, not with a single solved answer inside, but with something better, a shape, a region between Mars and Jupiter, a place mostly made of space, a total mass smaller than the Moon, orbits too stirred to be original, compositions too mixed to be simple, gaps cut by resonance, families born in collision, some of those families young enough to remain clear, others ancient enough to have blurred into the background. Ceres, round and water-touched. Vesta, differentiated and scarred. Pallas tilted high. Hygiea among the large survivors. Fragments drifting under sunlight. Small bodies spun by light itself. Stones delivered to Earth. Main belt comets hinting that even here the story of ice is not gone. Jupiter leaning over the whole scene like a force too large to ignore. And behind it all, the early solar system not as a calm assembly line, but as a history of movement, subtraction, and survival. I like to think that if you could stand somehow above the belt and see not only where its objects are, but where they have been, the region would glow less like a ring and more like a memory. Paths crossing, thinning, vanishing, some returning, some never meant to remain, some settling into long-term stability, like dust finally coming to rest on shelves after the floor has stopped trembling. Not perfect order, just enduring structure after disturbance. And that may be the gentlest truth in the file tonight. Not every system tells its history by preserving everything. Some tell it by what they cannot keep. Some tell it through the survivors that remain after the great rearrangements are done. The asteroid belt is one of those places, sparse, ancient, unfinished, and extraordinarily eloquent because of it. Back in the office, the window is still black, the mug long cooled, the folder still open beneath the light. The room has the same measured quiet it had at the start, but it feels a little different now. Less empty, more resolved. The chair, the desk, the space between them, all still separate, all still sparse, and yet unmistakably part of one arrangement. That is what the asteroid belt became for us tonight. Not a crowd, not a wreck, an arrangement. A surviving pattern of worlds and fragments that lets us infer the motions that shaped them. And so, at the very end, we can say it plainly. The asteroid belt is not the remains of a single lost planet, and it is not a dense gauntlet of stone. It is a sculpted relic between Mars and Jupiter, undermassive, dynamically stirred, compositionally textured, and still changing. It is one of the solar system's best preserved records of how planets form, how giant worlds migrate, how collisions create families, how fragments reach Earth, how water-rich material may have moved inward and how history can remain legible even after most of the original material is gone. That is the file tonight. That is the belt. And now, at last, we can close the case file.